Okay, as you sign our is I only for today. However, we will start talking about sets unless you have any questions regarding any problem that's really difficult in the exam. Unless you have any questions regarding the problems, maybe the practice, or something like that, we'll start with sets. Okay, I added these new items. Then we have this. I added it twice. And we'll start talking about sets. This is a file that I uploaded and I already have it here. So okay, so then do you have any questions regarding propositional logic, predicate logic? Then the test will be a week from today. It will be very similar to the two tests that I uploaded. Well, I uploaded only, two solutions and one without answers so that you can practice. So no questions? I wasn't sure about postponing the test. It means that it's true you have more time to practice, but also more time to forget what we have seen, so. But then you wanted me to postpone it, then I decided to do it. Okay. Then what is a set? If they stop talking, maybe I can start the class. Okay, question?
Maybe a series of elements that are united, they all share a characteristic.
Was that a question?
No, that was.
Regarding what is it set? Yeah. Then you are already in class. Since they were all talking, then I didn't know that you were already in class. Yeah. It's a set of objects or things that are united with certain characteristics. That's the real definition. Because there are two ways of defining a set. By extension, let's say the set that contains 1, 2, and 3, or the set that contains 1.1, 1.1, 1.2, 1.4, minus 0.3 and 5, or by comprehension, which is what you just said, that it gives it the characteristic that unites all of those objects. For example, the set of natural numbers that are between 1 and 3, that's a finite set, 1, 2, and 3. However, the set of real numbers that are between 1 and 3, it's an infinite set. But what unites them is this predicate. X is between 1 and 3. We have special sets, the real numbers, the integers, the natural numbers, and the rational numbers. Axiom 1 is abbreviation. If you define a set by comprehension, For instance, the set that contains x sub 1, x sub 2 till x sub n, it's in fact an abbreviation for the x's such that x is equal to 1 to x sub 1, or x is equal to x sub 2, or x is equal to x sub 3. For instance, the set that contains 1, 2, and 3, it's just an abbreviation for saying all of x's such that x is equal to 1, or x is equal to 2, or x is equal to 3. Then what matters is this predicate here, which is the characteristic predicate, which tells us if an element belongs to the set of or not, which tells us if that predicate is true for x, then the element belongs to the set. Now, there are a few things that we know, but that we can prove knowing that in fact a set has a predicate which characterizes it. Sets do not contain repeated elements. That means that a set that contains A and A is equal to a set that contains only A. How do I prove that? I start with the set that contains A, and I say, oh, that's just an abbreviation for the set that contains, it's all of the x's such that x is equal to A or x is equal to A. What can I do that? That's a trick question from propositional logic. What does it mean? X is equal to A or x is equal to A. What axiom can I apply there? No. You can't simplify an or. Idempotency, yeah? It means that P or P is equal to P. Then this is equal to X is equal to A, and then by abbreviation, that's the set that contains A. So then sets do not contain repeated elements. Yeah. In sets, the order is irrelevant. What do you think I will do here to prove that the order is irrelevant? Yeah, you use a commutativity of OR. So first you have A and B, then by abbreviation, that's X such that X is equal to A or X is equal to B. By commutativity, that's X is equal to B or X is equal to A. And by abbreviation, that's the set that contains B and A. So in a set does not contain repeated elements, and in a set, the order that does not matter. What matters is membership. And you denote that with an epsilon here. X belongs to S. Now, if I define S as the set that complies with predicate P, or that makes predicate P true, then when I am saying that X belongs to S, in fact, I am saying that P of X is true. Notice this here this is a Boolean expression. Its value is true or false, the same as a predicate. Then X as an element of S is equivalent to saying P of X is true. Now, what else can I say? Then I know. If I want to say that there exists an X that belongs to S, then it's the same as saying there exists an X that makes P true. If I want to say that all x's belong to S, it's the same as saying for all x, px. And also, if I want to say that there is an x in S such that Q is true, it means that there is an x such that P of X and Q of X. And if I know that for all x in S, QX, it's the same as saying that for all x, if P of X, then Q of X. Then there is a relation between sets and the predicate logic. So then the first examples we'll work on here will in fact be like a review, like a summary of things that we've done with predicate logic. Now, this is a lemma, which is the following, which is very useful, and it seems that it's difficult to prove, but it's obvious and it is true. If X is a set that has a single element T, that means X is a set of all X's such that X is equal to T, and there is an X in S such that R of X, then I can conclude that R is true for T. How would I prove that? I have S is equal to the set that contains T, and there exists an X in S such that R of X. This is my hypothesis. By Leibniz, I have S is equal to something, and I have another predicate here. That means I can replace the right-hand side of this equivalence for S in this equation, applying Leibniz. That means there is an X, there exists an X in this set such that R of X. Now, by sets and quantifiers, what I said, if there exists an X in S such that Q of X and the characteristic predicate of S is P, then I know that there exists an X such that P of X and Q of X. So here, I just removed this membership clause, and I just left X equals T, and I say there exists an X equal to T such that R of X. And by one point rule, I get R of T. Here, it seems strange. The only new thing I'm using is this. Membership is what matters, and predicates and sets. And this way, what I proved is if I have a set that has a single element, which is T, and I know that there is an X in S such that R of X, then I know that R of T. The strange thing is that the same thing happens with the for all. Why? Because the for all, in this case, since there's only one element, then for all is equivalent to their existence. Again, S is equal to the set that contains T, and for all X in S, R of X. Then I can replace S for the set that such that X is equal to T, and by predicates, and then X such that X P of X, I just replace P of X here. And then where I have here is, again, one point rule and R of T. Now, I'm going to talk to you about a paradox. I'm going to solve this paradox, or rather tell you how the mathematicians of the early 20th century solved it, and then we'll go on to other problems. The interesting thing is that with this proof, we'll review some of the things that you need for your first exam. Bertrand Russell, at the beginning of the last century, said, well, let me start with a bit of history. When they were talking about axiomatizing mathematics and, well, discrete math, or any math for that matter, they started saying, well, the most basic things are sets. But the only definition they had of sets is the one that I gave you right now. A set is an unordered collection of objects. And they said, okay, membership is what matters. So then you define a set like this. You always define a set like this. S is a set of all x's such that P of X. X's, those x's can be integers, they can be numbers, they can be sets. In fact, they can also be sets. And then we would say X is, then that's the only way they define sets. But if I decide that I want to define sets that way, then I have a problem, which is the Russell paradox, which is the following. Consider the following set. W is the set of all sets that don't belong to itself. That means that for any set, if S belongs to W, it means that S doesn't belong to itself. But W is also a set. That means that if W belongs to W, then W does not belong to W. obviously the way we define sets is ill-defined because we can arrive at a paradox. The idea is not to change the way we define sets, but to give certain axioms that tell me that a set defined like this is not well defined. So then Zermelo-Franken decided that they were going to axiomatize sets. They defined many axioms, but the ones that we're going to use are only two, maybe three. And then these, and with these two, I can show you that Russell's set isn't a set. Let's say pairs. If S and T are sets, the set that contains S and T is also a set. Notice that I'm not saying that S and T have to be different. I'm just saying S is a set and T is a set, then the set that contains S and T is also a set. Now, this is an axiom that is not easy to understand, but then let's start with this line here. A member M is a member minimal of S, or is a minimal member, but it's called member minimal. They switch these two things around. If M is an element of S, and for all x's in S, X does not belong to M. I'm going to show you a few examples. Now, this is a set that contains two elements. One element is a set that contains A. The other element is a set that contains A and the set that contains B. And I have some other sets here. It doesn't say that an element that a member minimal is an only, it's unique. Let's say, notice that the set that contains A is not a member minimal element of S. Why? Because there is, and for all X element of S, then X does not belong to M. Notice that using generalize De Morgan, for all x's, X element of S, X is not an element of M. It's the same as saying there does not exist an element of X that is an element of M. Right? If I'm writing for all X, X is such that X is an element of S, X is not an element of M. That's the same thing as saying there is not an element of X that is an element of M. By generalized order. So what I'm saying here is that for all that M is a member minimal of S, if M is a member of S and there are no other member of S is a member of M. So A would not be a member minimal because A is a member of the set and it's also a member of the set that contains A. The set that contains the set that contains A and the set that contains B is not a member minimal. The set that contains the set that contains A is not a member minimal. Now we have two member minimals here, which are the set that contains B. B is nowhere here in the elements of S, and A is also a member minimal. They don't have to be sets. Using that definition, this set would have two member minimal elements, which would be the set that contains B and A. What I'm saying, the axiom says that every set that's not empty has at least one member minimal element. It's the only axiom, which sort of sounds like the well-ordering principle, which states that any non-empty set of positive integer numbers has a minimal element. It sort of sounds like that because we can always order the sets by membership. But anyway, that's the member minimal, or it's called the regularity axiom. Okay. Now, starting this way, I'm going to define a set, any set, and I'm going to come to the conclusion that that set cannot belong to itself. Now, I'm going to prove that S cannot belong to itself. I start with C, an arbitrary set. Let C be an arbitrary set. Let T, I'm going to define two variables, T and C. Let T equals C and S equals C. Remember the pairs axiom. If S and T are sets, then the set that contains S and T is also a set. C is an arbitrary set. I define S and T equal to C. Then by the pairs axiom, the set C prime, which is the set that contains S and T, is also a set. Since T equals C and S equals C, then replacing using Leibniz, C prime is equal to the set that contains C and C. But since sets do not contain repeated elements, by definition, because we define them by giving them a predicate, then C prime is equal to C. By the regularity axiom, I know that there is an M in C prime that for every X in C prime, X does not belong to M. Since X has a single element, then it must be C. Of course, we could have done this using this axiom without writing this down like this. Using this axiom, if it has a single element, then I know that it's true for that element. Then I know that C is an element of C prime, and for all x's, X in C prime, X does not belong to C. We can instantiate X equals to C this way. And here I say, if C is an element of C prime, and I do instantiation here, and C element of C prime implies that C is not an element of C. Then by modus ponens, C is not an element of C. Notice that the only thing I assumed was let C be an arbitrary set. And using these two axioms, I concluded that C cannot be a member of C. In fact, I could have written it out like this. Right I have it like this. Now, remember our theorem that says that if I have if there exists an M is in a singleton set, and such and like this for all x in C prime, not x in M. That means that in fact, I can apply this rule that I have here, this one. If I know that S is this set and X only contains one element, then I can just conclude R of T, which is what I'm going to do right now. This means that I can rewrite this as M in C such that S is equal to C. Then I'm going to replace M for C. Then I would write for all X in C prime, then not X in C. But again, what is C? C is this. C prime is this. That means applying the same theorem, but this time for all, then I would get that this is equal to not C in C. And the only thing I assumed was that C was a set. That means that if C is a set, C cannot belong to itself. The only thing that they did was define axioms such that the axioms would show that Russell's set was impossible. So now, knowing that Russell's set is impossible, then I go on and do this. Let W be a set defined as follows. W is a set of all S such that P of S, where P of S is that S does not belong to S. Does not belong to S, yeah. Assume W is a set. We just proved that W does not belong to W. Therefore, P of W is true, so W belongs to W, giving us a contradiction. What was the only thing we assumed? That W was a set. Before Zermelo-Fraenkel, were ill-defined, that this set, Russell's set, was ill-defined. But then they couldn't really prove that it was ill-defined until they axiomatized what sets were, and then they did prove it. It's not cheating or anything, but they did have to give a definition of sets such that Russell's set was impossible. So, now, let's start looking at different properties of sets. Membership and non-membership. We have X is a member of A, and we write it like X with that epsilon there is a member of A. X is not a member of A. We cross out the membership symbol, but in fact that is the negation of X is a member of A. We have two special sets. The universe, which contains all elements in the domain, and the empty set. X is, if we are talking about sets over a domain, sets of sets, or any set, or the universe of all possible sets, X is a member of the universe is always true. X is not a member of the universe is always false. The set that does not contain any elements, or that contains no elements, it should say here. X is not a member of the empty set is true. X is an element of the empty set is false. So now we have that A is equal to B. If what matters is membership. We want to know when two sets are equal. Two sets are equal if what happens if for all the elements of a domain, X is an element of A, if and only if X is an element of B. Now we're also interested in subsets. A is a subset of B if every element of A is an element of B. However, there may be some elements of B that are not elements of A. However, there is also the concept of proper subset. A is a proper subset of B if A is a subset of B and A is not an element of B. Now, let's suppose our universe is, let's see if I have an example here. I don't remember. No example, so then I'll write the example here. Let's say that my universe in this case is I have A, the set that contains 0, 2, and 4. E is the set of y's in the universe such that y is even. Note that here, if X is a member of, I can say that that A and E are equal. X is an element of A if X is 0, 2, or 4, and X is even numbers in U are 2, 4, and 0. Then it would be the same set. Now, A is a subset of E because if X is a member of A, then X is a subset. Then X is a member of E. But if I write this here, B is 1, 1, 3, excuse me, 1, 2, 1, 2, 4, 0. Then A is a proper subset of B because it's not the same set. We have some properties. I mean, some functions over sets, some operations over sets, which are union, intersection, difference, and complement. Let's start with complement. X is a member of the complement of A. Oh, and in all of the exercises, you don't use the complement sign, but you use a superscript A as C. You write it like this, A, C, which is, I wonder if I can use a superscript here. No. Anyway, you say A to the C instead of this. You use a superscript when your class notes and other things. So X is a member of the complement of A if X is not a member of A. X is a member of the union if X is a member of A, or X is an element of B. X is an element of A if of the intersection if it's a member of both. And of the difference if it's a member of A, but it's not a member of B. You usually use Venn diagrams, though I don't really like to use them, which is something like this. if the blue one is A and the red one is B, then if I have something like this, then the union would be what's in both. The intersection would be, oh, the thing is, I don't think I can do it this way. You can't really see it. If I let go of it, then it would be the one what is like the purple when I'm putting it like this. And then the difference would be what is left here with blue. Format. And mm, there, then that's better. Then the union would be both of them here, and the intersection would be the one that's right here just with blue without counting this. And if I put something here without, but then I want this not to be green, but to be another color. I think I should. Don't I have a half moon here someplace? Or maybe transparency? You see transparency someplace? No. Where do you see? Oh, yeah. Sort of. See? So there we can see some different colors there. So then, though, if you were working with more sets, using Venn diagrams, sort of like using truth tables, isn't an option. So then we could look at it there, but it's not a good idea to use Venn diagrams. In both. Intersection are things that are in, no, that are in one or the other. So if we look at the drawing here, the union would be the union of the two circles. The intersection would be this, the part in the middle would be the intersection. If I wanted to say, the complement would be everything that's green. And if I wanted to say the difference, it would be the thing that was left blue with this like 3/4 of a moon here. Like a, Here I have an example. So I hope this example is right. I hope there are no mistakes here. If my universe is the digits from 0 to 9, and A is 1, 2, 3, 4, and B is 3, 4, 8, 9, then the union would be 1, 2, 3, 4, 8, 9. The intersection, there was a mistake. This should be the intersection, should be 3 and 4. The difference A minus B, I remove the elements of A that are also in B. B minus A would be 8, 9. Not the complement of A, this should be the complement of B, is 0, 1, 2, 5, 6, 7. Let's prove our first theorem using sets. I want to prove that the complement of A is A. We must prove that if I want to prove that two sets are equal, I must prove that if X is a member of one, if and only if X is a member of the other. Then X is an element of the complement if, by the definition of complement, if X is not I have to prove that X is not an element of the complement of, I have to prove if X is not an element, if X is an element of the complement of A, then it's an element of A. If X is an element of the complement of A, again, it means that it's not an element of the complement of A by the definition of complement. The definition of complement of not being a member, it's not a member. Now, if X is an element of the complement of A, of the complement of A, it means that X isn't an element of A. If X is an element of A, it's because it's not true that X is an element of A. And by double negation, it means that X is an element of A. Again, right now, I'm only applying my new definitions for being a member of for being a member of the complement, but then I'm just applying propositional logic to prove things. You see, I could do it this way. Okay. So, any questions regarding this example? Our next example. The same way that we have that we had our equivalence laws for the propositional logic, we have our equivalence laws for sets. Let's start with the equivalence laws for intersection. If I intersect A with a universe, I get A. If I intersect A with the empty set, I get the empty set. If I intersect a set with itself, I get A. If I intersect A, if I have that A intersection B, it's equal to B intersection A. I have that the intersection is associative. I have that that I can distribute the intersection over the union. I have De Morgan 4 sets, and I have absorption, and I have that the intersection of A with its complement is the empty set. Let's prove a few of these. Look how we prove De Morgan. If I want to prove that the complement of the intersection is the union of the complements, I have to prove that if X is a member of the complement of the intersection, then X is a member of the union of the complements. So then I start by writing X is a member of the complement. By the definition of complement, it means that X is not a member of the intersection. By the definition of not being a member is that it's not true that X is a member of the intersection. By the definition of intersection, if X is an element of the intersection of A and B, it means that X is an element of A and X is an element of B. Now I can use De Morgan. Why? Because De Morgan says not P and Q is equal to not P or Q, which there we just have placeholders. Then I have not X is an element of A and not X is an element of B, which by definition of not membership is that X isn't a member of A and or X isn't a member of B. This is or. And now I have, by the definition of complement, it means that X is an element of A or X is an element of B. And I didn't put the last line here, which is the definition of union. If X is an element of the complement of A or X is an element of the complement of B, it means that X is a member of the union of the complement of A and the complement of B. Exercise. Prove all of the rest of this table using the same thing that we've done here. Let's do a few of those, and they won't be since you can't take the board, then when you do it then it won't. So then let's do this one. This one. A intersection A union B is equal to A. To prove that, I would have to prove that if X is a member of A intersection A union B, that's equal to saying X is a member of A. This is what I have to prove. Again, very important, don't forget parentheses. Then I have X is an element of A, and in parentheses, X is an element of A, or X is an element of B. Now, what do we have here? What we have here is square and square or triangle, which is what? Absorption. B by absorption, when you would have X is an element of A, which was what we wanted. So as you see, when we're working with sets, in fact, we are working with propositional logic. Now, let's assume that we've already proven these 1, 2, 3, 4, 5, 6, 9 theorems. We already proved all of them. These we proved using the definition of union and intersection and everything. Now, I have these other equivalence axioms, but these I'm going to prove in another way. I want to prove that A union, the empty set is A union, the universe is the universe, A union A is A union B is B union A. You have associativity, distributivity, you have De Morgan, the other De Morgan, because we just proved De Morgan of and you have absorption, and you have complement. I'm going to prove De Morgan of the union. So here, similar to what I did for propositional logic, I'm going to start with the right-hand side. I double complementation. I get this, the complement of the complement. Now I take only this part and I apply De Morgan, which I just proved the complement of A union the complement of the complement of B. By double complementation, I get A union B. This proof is very similar to the one that I showed you when I proved the opposite. I think I proved it for I proved it for and using that I had it for or. Now, let's see some more complicated proofs. I want to prove that if A is an element, if A is a subset of B, then A intersection B is equal to A. We must prove that. I'm going to translate this. If X is a member of A implies X is a member of B, then X is an element of A intersection B is equal to X is a member of A, which is the same as proving, to prove this, I'm using propositional logic that if X is a subset of B, then if X is an element of A intersection B, then X is an element of A. If X is an element of, if A is a subset of B, then if X belongs to A, then X belongs to the intersection. Of course, this always happens. What I have to prove is the top part. Oh, and we did, which we don't have the proof here. We have to be very careful when we're using this. This only works because I'm working with a universally quantified X, but I'm working with and. If it were with or, it wouldn't always work. So let's try and prove this. Oh, I'm going to prove it the other way. Yeah. Okay. We must prove this. Let's prove it, although then I'm going to show you an easier way to prove it. So I want to prove X is an element of A, then X is an element of B, and X is an element of A intersection B. This implies that X is an element of A. So that my hypothesis would be X is an element of A, then X is an element of B, and X is an element of A intersection B. These are my two hypotheses, and I want to prove that X is an element of A. But in this case, it's very easy. Definition of intersection applied to 2. I get this. And by simplification, I get that X is an element of A. In this case, it's easy. Because, in fact, if X is an element of an intersection, then X is an element of any of the two sets in the intersection. Now, this one is harder. I have X is an element of A implies X is an element of B. I have X is an element of A. I have my hypotheses. Now, what can I do with this if X is an element of A, then X is an element of B. I have my hypothesis that says X is an element of A. What can I conclude with these two statements? If X is an element of A, then X is an element of B. I know that X is an element of A. What can I conclude? Five close quotes 1 and 2. Now I can compose these two. X is an element of A and X is an element of B. Composition 2 and 3. And here I have definition of intersection. X is an element of the intersection. Then this is a quite easy proof. I'll turn on the light later so you can maybe copy it or take a picture of it, but then you could do it also like this.
Excuse me, Professor, the first step, what does it say?
Composition. It says X is an element of A and X is an element of B. I take this one and this one. And I compose 2 and 3. And this is the definition of intersection. Now, I can define a set A is a set of elements in the universe that make its predicate true. I can define B as a set of elements in the universe that make the predicate piece of B true. The universe is a set of x's such that true. The empty set is the set of x's such that false. That means it's the empty set. Not A is a set of x's in U such that not P of A. The union is PA or PB. The intersection is PA and PB. And the difference is PA and not PB. If we use this representation, we can prove many things very easily, as we did in the propositional logic, with a caveat that I'll tell you later on. Replace false for the empty set, true for the universe, not P sub A for the complement, P of A and P sub B for the union, P sub A and P sub B for the intersection, P sub A and not P sub B for the difference. The meta theorem says that A equals B is valid if and only if P sub B is valid. A is a subset of B is valid if and only if P sub A implies P sub B. A is the universe if P sub A is valid. A is the empty set if and only if not P sub A is valid. Translating all the theorems, we have theorems that we had in the propositional calculus, but we have to be very careful. We can't mix and match things that are written in propositional logic and predicate calculus and just translate a part of them. I'll show you an example. In this case, I want to prove that A is a subset of B if and only if not B is a subset. The complement of B is the subset of the complement of A. We must prove that P of A implies P of B if and only if not P of B implies P of A. And that is, what is that theorem? the contra positive, then that is true. Now, I want to prove that if A is a subset of B, then A intersection B is equal to A. Then what I have to do is prove that P sub A and P sub B is equal to P sub A using the fact that P sub A implies P sub B. So here I'm using simplification, but I'm using the whole simplification. I'm not using simplification of a part, but I'm saying P sub A and P sub B implies P sub A. This whole expression is true. I'm not saying P sub A and P sub B implies, I'm not replacing P sub A and P sub B for P sub A. I'm replacing this whole expression for true because this is simplification. And P sub A implies P sub A and B. Now, P sub A implies P sub A and P sub B by distributivity. It's P sub A implies P sub A and P sub A implies P sub B. This is true, and P sub A implies P sub B by identity, and this is my hypothesis. I could have done it easier using what I just proved before. Now, it was possible to use this because the meta theorem is just shorthand for this. Look, it's shorthand for all x such that, and I could do it. Now, suppose you wanted to prove this. Example of an incorrect proof. Suppose that A is an element of the union of B and C, and that's the same as saying that A is an element of B, or A is a subset of B, or A is a subset of C. This seems to be true because by the meta theorem, I would have to prove that P sub A implies P sub B or P sub C is equivalent to P sub A implies P sub B or P sub A implies P sub C. This seems to be true. This, in fact, is a theorem of the propositional calculus, but it isn't. It isn't, but because what we have is this. You have to make sure that you know that we're doing this. For all P sub A, for all x, if P sub A, then P sub B or P sub C is equivalent to P sub A, then P sub B or P sub A, or for all P sub A, then P sub C. And this is not true. This is not valid. Because what we have is that we can do this, we can apply distributivity, or not this, yes, distributivity, if this were an and, if this were the same operator as we have here. And this is not true. Let me show you an example. Let's see if this is an example. No? I'll show you an example. Let's say that A is equal to is it true that A is a subset of the union of B and C? Yeah, but we write it here so that we have it. So we can see that A is a subset of the union. The union is what 1, 2, 3, 4, but A isn't a subset of B and A isn't a subset of C, then it's not true. Okay, so next class, we'll go on, we'll continue talking about sets and examples. And if you have any questions for your midterm, then we'll answer them, okay?
What is the midterm rule?
A week from today.
Yeah, why? Everybody did.
No, but the many people asked me if we could move it, and then I discussed it with with Miguel, and since we already got ahead in class, then I didn't need to use your lab session, so you can keep on playing the game and you won't run behind with the game. Okay? We could have done it on Thursday, but then I decided to move it to Monday. Okay. Anyway, we are far behind, even though.